Gradient boosting is one of the most powerful machine learning algorithms, but most explanations miss what it's actually doing. In this video, we'll build it step by step, from intuition to the full math. It can be applied to both regression and classification tasks. The basic idea of gradient boosting is that we start with a constant baseline prediction, such as the mean of the data for regression, and then iteratively add trees that are fitted to the errors of the previous predictors. This is different from random forests, where each tree is trained independently. As a result, gradient boosting often produces a stronger overall model than random forests. As with any machine learning model, our goal is to find a function that minimizes the expected value of a loss function. Gradient boosting for regression is more straightforward than classification, so we will start with it. For regression, the most common loss function is the mean squared error. The factor of 1/2 is included to simplify the derivatives later. So the first step of gradient boosting is to find a constant baseline prediction that minimizes the loss. For mean squared error, this constant is simply the mean of the target values. Here is a short proof of that. You might be wondering why it is called gradient boosting. It is because we take derivatives with respect to the predictions. This formula may look complicated, but the idea is simple. We take the derivative of the loss function with respect to the model's predictions and evaluate it at the current predictions. That is what the subscript represents. Since gradients point in the direction of steepest descent, we negate them to obtain the direction of steepest descent for the loss. These values are called pseudo-residuals, and they are what we fit the new trees to. They are called pseudo-residuals because, in regression, they are exactly equal to the true residuals, meaning the difference between the actual and predicted values. For classification, they are not exactly the same, but they have a very similar form and closely resemble residuals. This is extremely important. We are not fitting targets, we are fitting the pseudo-residuals. Here's a quick derivation showing that, for mean squared error, the pseudo-residuals are equal to the true residuals. The next step is to train a decision tree on the pseudo-residuals. In the formulas, you may see notation like RJM. This refers to a decision region, meaning the set of feature value ranges that define a leaf. Here, J is the index of the leaf within the tree, and M is the index of the tree in the sequence, also known as the boosting iteration. The leaf values are chosen so that, for each leaf in the new tree, adding that value to the previous predictions minimizes the loss function. This optimization is done using only the data points that fall within that leaf's decision region. In other words, each leaf learns the best correction term to add to the current predictions so that they move closer to the true values on average. For the mean squared error loss, these leaf values turn out to be simply the average of the residuals within each region. Here is a simple derivation of that. After computing the leaf values, we update the model by adding them to the previous predictions, scaled by a learning rate, typically around 0.1. This scaling helps prevent overfitting and stabilizes the optimization process. Although the formula is written as a sum, for any given input, only one term is active, since each input falls into exactly one decision region, and the indicator function is 1 only for that region and 0 for all others. Now let's visually see how a gradient boosting model iteratively reduces its residuals, with the learning rate set to 0.1. As in previous videos, let's compare the training and testing errors as we increase the number of estimators, in this case trees, in gradient boosting. As you can see, unlike random forests, the training error tends towards 0 and will eventually reach exactly 0 given enough trees, as long as the tree depth is greater than or equal to the number of features in the data. We have now covered gradient boosting for regression. Before moving on to classification, there is an important issue to address. Even in classification, we are still fitting trees to pseudo-residuals, which are numerical values. This means we must use decision tree regressors, not classifiers. If we were to directly build an additive model for probabilities, the outputs could fall below 0 or exceed 1, which makes them invalid as probabilities. It would also lead to slower and less stable optimization, even though it could still work in principle. Instead, we use something called link functions. We will start with the regression case. Even though it is not strictly necessary, it provides useful background. We begin by modeling the distribution of y given x. For regression, this is typically assumed to be Gaussian. The most likely value of y, which is what the model predicts, lies at the center of the distribution, which is the mean. As the true value moves further away from this mean, its probability decreases. Here, mu represents the expected value of the target given x, not the mean of x. Once we have the probability for a single sample, we multiply these probabilities across all samples to obtain the likelihood of the model parameters, since the predictions depend on them. To find the optimal parameters, we maximize this likelihood. However, working directly with products is inconvenient, so we take the logarithm, which converts the product into a sum. Since the logarithm is monotonic, this does not change the location of the optimum. We now maximize the log likelihood. Since most optimization methods are framed as minimization problems, we instead minimize the negative log likelihood. Also, the variance term is treated as constant since it does not affect the optimal parameters, so its contribution can be ignored. This leads directly to mean squared error, which is the standard loss function for regression. This procedure to find the loss function given a probability distribution is called maximum likelihood estimation. Now, what is a link function? A link function transforms the target into a space that is easier to model. Typically, it maps values to the entire real line and is continuous and strictly monotonic, so it is invertible. There are many possible link functions, but to find the most natural one, we express the distribution in exponential family form. For the Gaussian distribution, when written in this form, the natural parameter turns out to be proportional to the mean. This means the link function is simply the identity function. That is why in regression, we did not need to explicitly introduce link functions earlier. Now let's find the loss and the link function for binary classification. The target in binary classification is assumed to follow a Bernoulli distribution. Here, instead of mu, we use p, which is the probability that y equals 1 given x, because in this case, they are equivalent. We repeat the same procedure, maximum likelihood estimation, to obtain the negative log likelihood, which gives the binary cross-entropy loss, also called log loss. The link function becomes the logit function. Logit is the name of the function, while its output is called the log odds, since it is literally the logarithm of the odds. A function you will often see in the context of binary classification is the sigmoid, which is used precisely because it is the inverse of the link function. To clarify, other link functions are also possible, as long as they satisfy the required criteria. In practice, they are also chosen to be continuous and differentiable. The logit is simply the most natural choice and leads to the simplest formulas. To summarize, here is a table of the loss and link functions used in regression and binary classification. Loss functions are not arbitrary. They arise from applying maximum likelihood estimation to a chosen probability distribution. Link functions, on the other hand, come from the natural parameter in the exponential family form of that distribution. Now let's see how link functions are applied in gradient boosting for classification. As with regression, our goal is to find a function that minimizes the expected value of a loss function. However, the loss is not defined directly between f and y. Instead, it is defined between the predicted probability p and y using cross-entropy loss. Here, f represents the logit of p, also known as the log odds, and p is obtained by applying the sigmoid function to f. Before continuing, let's derive the pseudo-residuals. We start with the loss function. Now we take the derivative. The result is simply p minus y. It is worth remembering this as we will use it in later steps. The pseudo-residuals are the negative of this, so they are y minus p. These may look like true residuals, but note that the model is predicting f, which is the logit, not the probability p. For later use, we will also need the second derivative, so let's compute that as well. Now we need to find a constant baseline predictor. For binary cross-entropy loss, this turns out to be the baseline log odds, which is the logarithm of the number of positive samples, where y equals 1, divided by the number of negative samples, where y equals 0. Here is a derivation of that. After fitting the decision trees to the pseudo-residuals, we need to compute the leaf values that, when added to the previous predictions, minimize the loss function. In regression, this was simply the average of the residuals. However, in classification, this is no longer the case because the residuals are in probability space, while the model's predictions are in log odds space. In fact, there is no closed-form solution for these leaf values. Instead, we approximate them using Newton's method. You may also see this derived using a second-order Taylor expansion. These approaches are equivalent, since Newton's method is also a second-order method, and it's simpler to derive the approximation using it. A quick overview of Newton's method. It was originally developed to approximate the zeros of a function, but since the minimum of a function occurs where its derivative is 0, we can also use it to find minima. When used for finding minima, it is a second-order method, meaning it uses both the first and second derivatives. When used for finding zeros, it is effectively a first-order method. This makes it faster to converge than gradient descent, but also more computationally expensive. The update formula is shown above. Now let's apply it to our problem. Here, G and H stand for the gradient and Hessian. In reality, they are just the sums of the first and second order derivatives, although in machine learning, the terms are often used interchangeably. If we take one step using Newton's method, we get an approximate value for the leaf outputs. You might wonder why we do not take more steps. The reason is that we are already working within an iterative algorithm, and the benefit of adding another tree is greater than taking multiple Newton steps, so we only take one step per iteration. Updating the predictor function is exactly the same in classification as in regression. The only difference is that the model now predicts log odds, so to convert them back into probabilities, we apply the sigmoid function. As we did with random forests and decision trees, let's plot the accuracy of the model as we increase the number of trees. The main difference compared to random forests is that the training accuracy approaches 1, and will eventually reach exactly 1 given enough trees, as long as the tree depth is greater than or equal to the number of features in the data. Gradient boosting does not require decision trees as its base learner. In principle, other models such as linear models can be used. However, in practice, decision trees are almost always used. This is because they are nonlinear, robust to outliers, and fast to train. In practice, shallow trees are typically used, usually with a depth of less than 6. The tree shown here has a depth of 2, where the root is not counted in the depth. Having too many trees can often lead to overfitting, unlike in random forests. To combat overfitting, we use techniques such as early stopping or a small learning rate. If you are wondering why we use a learning rate instead of simply adding the full corrections predicted by each tree, it is because it has been empirically observed that scaling these corrections down improves generalization at the cost of requiring proportionally more trees. If we want to further prevent overfitting, we can use stochastic gradient boosting, where each tree is trained on the pseudo-residuals of a random subset of the data. We have covered regular gradient boosting, also known as Friedmann gradient boosting, but it is not commonly used in practice anymore, as more optimized versions exist that almost always outperform it. The 3 most popular ones are XGBoost, which uses regularization, histogram-based methods, and serves as a strong general-purpose baseline. LightGBM, which is designed for large numerical datasets and high performance. And CapBoost, which is specifically designed for datasets with many categorical features. I will cover these 3 in a future video. Let's summarize the steps of gradient boosting. We start by initializing a constant baseline predictor. We then build M trees, where M is often on the order of 100. At each step, we compute the pseudo-residuals and fit a tree to them. We then compute the leaf values for that tree. Next, we update the model using these leaf values. After repeating this process, we obtain a strong predictor. Gradient boosting, especially its optimized variants, is considered one of the most powerful classical supervised machine learning algorithms. Gradient boosting is just iterative error correction, guided by gradients. Once you see it this way, everything else falls into place. If you liked the video, please subscribe.